Okay, let's start. This is going to be our last lecture. Remaining of the course would be paper presentation. Okay, today we are going to learn about restricted Boltzmann machine. Restricted Boltzmann machine basically is the first model. It's a building block. It's not by itself, a neural network or deep network. It's a building block for making a deep network. The first paper in 2006, the paper that basically was the beginning of deep learning, had this structure as a building block, Boltzmann machine. But maybe the reason that we do it last among all of the other topics is that in spite of the fact that it was the first model, rarely is used at the moment. The idea started with this, but it's not that common anymore. Okay, restricted Boltzmann machine is unsupervised model, and you have two layers. It's undirected graphical model. You have a visible layer and you have a hidden layer. So basically the idea is that given this visible layer, given the input, I would like to have a representation of the data in a different space. So you give me a data in 1, 2, 3, 4, 5, five-dimensional space. I would like to have a representation of the same data in seven-dimensional space. So you're familiar with the concept of dimensionality reduction. You have seen PCA as a linear dimensionality reduction. You have seen nonlinear variations of dimensionality reduction. And in all of them, you map the data in a different dimensional space. And one basically interpretation of what we are doing in dimensionality reduction is that we have a hidden variable and we have an observation. And given the observation, we are inferring that hidden variable. And this hidden variable could be in different dimensional space. So you can look at restricted Boltzmann machine the same way, that it's a method to represent the data in a different dimensional space or have a different representation of the data. So it's totally unsupervised. It's called restricted because original Boltzmann machine, this restricted Boltzmann machine is like a bipartite graph. So this is, say, for example, hidden, and you have observations, and there are undirected links between hidden and observation. But there is no link between units of each layer. So this variable has no connection to this variable. In the original Boltzmann machine, there are some connections between these units. Restricted Boltzmann machine is basically a model which restricts this type of connection. And there's connection only between hidden and observation, not between units of each layer. Okay? So the way that given V observation, we infer the hidden variable is by defining a distribution function, probability function over this, and infer the most probable observation given that model. The model is energy-based model, and there are many energy-based models that I'm sure you have seen. So the idea is that we can define a joint distribution or observation and hidden variable of this form. When E is energy function. So I'm going to define an energy function. My goal is that the energy between this configuration of the data observation and hidden is as low as possible. this type of models has been motivated in physics originally. And that's why we have the concept of energy, because in practice, they really, physically, they had this concept. And they wanted to define a probability over this concept, and they defined the probability on this form. So you have a function of energy somewhere, just make exponentiate this function, exponential of the negative value of this function, interpret this as probability. And if you want to interpret this as probability, you need to normalize it. Divide by a normalization factor to make sure that summation will be 1. Okay, so this is our joint distribution over observation and hidden variable, which we call it energy function. An energy function is defined on this form. V is our observation, which is a vector, and H is our hidden variable, which is a vector, could be in different dimension. And B, C, and W are our parameters of the model. B is a vector, is a bias vector, C is a bias vector, and W is a matrix. And Z is a partition function or normalization function, which you needed to make sure that it sums to 1, which is summation over all possible values of V and H. Okay, let's see how these parameters work and what's the meaning of these parameters intuitively. As I said, W is a matrix. Basically, is a matrix of, all of these weights. A matrix of the size of this matrix times the size of this vector times the size of this vector. And B is a vector of the size of V, and C is the vector of the size of H. It's biased. So if I rewrite this energy function in a scalar form, basically I have a dot product here, which I can write it explicitly as summation of elements of the vector B and vector V, and elements of vector C and vector H, and so on. Restricted Boltzmann machines are usually trained on binary data. There are variations of restricted Boltzmann machine for real valued observation, but 90% of the time it's on binary data, and the model that we are discussing now is for binary data. So V and H are binary data, could be 0 or 1. The values could be 0 or 1. Okay, so suppose that this B is negative. What's going to happen? I need to minimize the energy, or I need to maximize the probability. I need to minimize the energy. So I prefer low energy. So this is the energies. So I will prefer, the negative of this to be large. So plus, 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 this value should be large. So if B is negative, I'm talking about V now. B is going to be multiplied by V. Bk is going to be multiplied by Vk. If Bk is negative and you want to maximize the negative value of this energy, then what Vk is going to be? Yes? 0. I mean, if you have two choices, V can be 0 or 1, and B is negative, then to minimize the energy, V should be 0, right? If B is positive, then, and you want to maximize this energy, minimize this energy, or maximize the negative value of this energy. Suppose, the negative value, all of them are positive now, and you want to maximize it. And now B is positive. Then you prefer V to be 0 or 1? Yeah, 1, right? Because you want a large value. Larger value is better, it is preferred. So we can think of B as a way to express your preference over the value of v. If b is negative, means that you prefer v to be 0. If p is positive, means you prefer v to be 1. Okay? So the same thing here for c. Negative c is a way to express your preference over the value hj to be 0. And positive value for cj is a way to express your preference over hj to be 1. Okay? So this is the role of these two parameters. And we have another parameter which is w. Now think of wjk and suppose that wjk is negative. If wjk is negative, what can you say about hj and vk? You want they are either 0 or 1. If it's negative, you want them to be 1.
Either of those must be, one of those to be 0. Hj or vk.
Mm-hmm.
One of those, you want one of those to be 0, preferably.
You're right. See, you have 3 terms. You have bk, vk plus cj, hj plus, this is our third term, wjk, hj, vk. We would like to maximize this. And this is negative. Okay? If I want to maximize this, and this is a negative value, I don't want this be a negative term contribute to my cost function. I want to cancel it out. So I prefer either h or v to be 0, right? Or both of them. So wjk being negative is a way to express my preference over the value of hjvk, that one of them should be 0 or both of them should be 0, either one. What about if wjk is positive? Both of them 1, right? So I prefer that both of them are 1 if wjk is 1. So wjk is a parameter which shows a connection between this pair of random variable. How do I want to connect them? So this is my model. It gives me some freedom over the value of h given the value of v. I have freedom to express, my preference over different values of h individually being 0 or 1 or in connection with v through w. Okay. And then, I told you that having this energy function, you can define a joint distribution, and this is your partition function. Okay. Unfortunately, computing this partition function, as usual in graphical model, is intractable. It's summation over v, summation over h, and you have exponentially many summations, in practice, and it's intractable to compute. So when z is intractable to compute, it means that computing this joint distribution is intractable because we can't compute the partition function. Okay, so we can't compute the joint distribution over v and h. That's the bad news. But the good news is that conditional probability is easy to compute. So easily I can compute probability of v given h, or I can compute probability of h given v. Okay? So this is intractable. The joint is intractable, but conditional is easy to compute. So if conditional is easy to compute and is easy to sample from, then how can I sample from the joint distribution? I know how to sample from h given v. I know how to sample from v given h. But I need to sample from h and v.
I think Gibbs sampling.
Gibbs sampling, right. the most obvious thing that you can do is Gibbs sampling. Gibbs sampling is, you just sample conditionally, and that would be joint. So that's the idea. I claim that it's easy to compute. Now I will show you that it's easy to compute, and then having this, it would be easy to sample jointly from this distribution. Okay, so
Why do you need joint over here?
sorry?
Why do you need joint? Like each layer be independent in the sense each layer is sort of an abstraction. So
For any model, if you want to do inference, you're going to need this joint distribution. If you want to be able, when we have graphical model, it means that we are modeling a joint distribution by definition. Graphical model is a way to model a joint distribution by adding some restriction, because if you have joint distribution over some random variable, theoretically you can answer any queries, any, okay? So if I have a random variable which is weather, rain, if I have joint distribution of this, then any query I can answer. What's the chance that tomorrow is rainy given that today is whatever, okay? Graphical model is a way to model the joint distributions. But since joint distributions most of the time is pretty hard to compute, a graphical model impose some constraint over, use your domain knowledge and impose some constraint over the joint distribution by imposing some independence between some of these variables. That's the main idea of basically graphical model. Okay. So, and here, if we would like to do inference, we're going to need it. If I want to compute this conditional distribution, it's going to be joint divided by PV, right? And it is basically 1 over Z e to the power of negative energy function, which is a function of V and H, divided by PV. But PV itself is summation over H of P, V, and H. Okay? So, let me write it here. So I have 1 over Z, and it's e to the power of this energy function was B transpose V plus C transpose H plus V transpose WH. Okay? Am I right? It was C was for H, right? And B was for V. Yes. Okay, so that's this term. And this term would be summation over H of E to the power of B transpose V plus C transpose H plus V transpose WH. And I have 1 over Z here. Because I can take this 1 over Z outside this summation, and I can cancel it with this one. Okay, so I can get rid of this partition function that was problematic. Now, this is E to the power of B transpose V times E to the power of C transpose H times E to the power of V transpose WH. I can do the same thing here. So it's E to the power of B transpose V times E to the power of C transpose H times E to the power of V transpose WH. And this is over H. This first term is constant with respect to H. Right? So I can take it out. I can put it here. And then I cancel it with this. So it's going to be e to the power of C transpose H plus V transpose WH divided by sum over H of e to the power of C transpose H plus V transpose WH. So I can write the conditional distribution of H given V as this form, and this is going to be some z prime, which is my partition function. Okay, you may think that, okay, we got rid of that partition function, but we have another partition function here to compute. But soon you're going to see that, you know, how can we in practice actually compute this very easily. So that was the steps that we had. 1 over z of this divided by PV, and then it simplifies to e to the power of C transpose H plus V transpose WH divided by some z prime. And if I write it in a scalar form, that's going to be the scalar form of this. Now, see, I have exponential of sum. So exponential of sum would be product of exponential, right? So I have exponential of sum. I can write it as product of exponentials. So basically, product of H given V is 1 over z prime, product of exponential of these terms. And H, J is one of the element of J. So what does it mean? It means, you know, it's very important. We have a very important property about H which is going to help us. So having this conditional probability over H as a product, it means that elements of H are independent from each other, right? So I can write the probability, the conditional probability of the first element of H given V times the probability of second element of H given V, and so on. So they're independent, which was clear from the graphical model either, you know, that given V, they should be independent. Okay. Any question here? Yes?
Could you repeat the last line you said about the independence on?
You know, here I have exponential of sum, right? So if I have e to the power of a plus b, right? It's e to the power of a times e to the power of b. So exponential of sum is product of exponential, right? So here I have exponential of sum. I can write it as product of exponentials, right? So if I have probability of if I have probability of A and B, and I can write it as probability of A times probability of B, means they are independent. If they are not, I have to write it as probability of A times probability of B given A. So this formula basically tells me that probability of H, which is, you know, a vector given V, is probability of H1 given V times probability of H2 given V times probability of H3 given V. So it means they're independent.
And J independent.
Sorry?
It is basically H J is a hidden layer.
It means that given V, elements of H are independent. If you observe V, given that observation, elements of H are independent. So you can do exactly the same for probability of V given H, and show that given H, elements of V are independent. It's symmetric, right? There's no difference between V and H in terms of this computation. That would be exactly the same. But I can, now I can compute the probability of H, one of the element of H given V. If I need probability of H given V as a vector, knowing that each unit is independent from the other one, I can compute the probability of one of these units and then multiply all of them together, right? So probability of one of the elements, like Hj, being 1, given V, just one of the elements, is joint divided by PV, right? And this PV is basically probability of HJV over all possible values of Hj. And over all possible values of Hj means probability that Hj is 1 plus probability that Hj is 0. Okay? So probability that Hj is equal 1 given V, we have it. Probability that H is equal to 1 given V, it's the same value. Probability that H is equal to 0 given V means that put 0, you remember what was the form? That was the form, right? Put H equal to 0. That's going to be e to the power of 0. So it's going to be e to the power of 0. Right? So probability of one unit of H given V would be e to the power of Cj plus V transpose W. And this notation basically means all rows, column G of V. And this is 1 plus e to the power of the same value. And it's sigmoid function, right? So probability of H, 1H, 1 unit, given V is just a sigmoid function of this form. And if you need the probability of vector H given V, because they're independent, that would be the just product of all of the J's. So that would be this product. That's going to be probability of H given V. The same for probability of V given H. That's this sigmoid function. Okay? Now, having these two probability of this form, it's very easy to sample from restricted Boltzmann machine using Gibbs sampling. So Gibbs sampling has two steps, as you know. In first step, given, say, for example, V, given observation, you sample H. Then given H, you sample V. And you just repeat this. And V and H that you have is samples of the joint distribution according to Gibbs sampling. But knowing that each of these units is just a sigmoid function and they're independent, help to first sample from each unit independently, so you can parallel sample all of these units. And it's very easy actually to sample. I give you an observation V. Given an observation V, suppose that the model is already learned. I know the W, I know B, and I know C. We haven't discussed this yet. I haven't told you how to learn the parameters of the model. But suppose that the parameters of the model is learned. I give you a V. It's very easy to compute this. You know the C, that's your observation, and you have W. And that sigmoid function of this, it gives you a probability. So the probability, say, is 0.2. Means that the probability that Hj is equal to 1 is 0.2. It means that you have to sample a uniform number, because it's like Bernoulli, it's 0 over. You have to sample a uniform number. So I sample a uniform number, in MATLAB just rand. And if this uniform number is less than what I computed here, then Hj is 1. Else, Hj is 0. So easily I can sample from that unit, and I can do it in parallel. I can do it for all of the units given the observation. And then sample for V. So it's very efficient, very easy to sample, and you can sample H and V. You can sample from the model jointly, easily. Okay, any question so far? So if this is clear, that we can sample from the model easily if the model is learned, I mean if the parameters of the model is known. Now our main question should be how to learn the parameters of the model. So I give you some observation, and so you have a bunch of V in your training data set. H is not observed, because it's hidden variable. So you just have set of images. That's your V. And you need to compute W, B, and C. Okay? So if you want to turn it off again, thank you. So how do we learn the model? The most obvious thing that someone can think of is to maximize the likelihood, the model, given data. So I define an objective function, which is just log likelihood of the model. And this is my observation, log likelihood of the model. I would like to maximize. But this P of our observation is in fact summation over H of PW and H, when H is my hidden variable. Okay? And this joint distribution can be written in terms of energy function. What happened here is that I had summation of t equal 1 to n of log of summation over all h of p, my observation t, and h. Okay? But this is basically 1 over z of e to the power of minus e h v. Right? This is constant. I can take it out. So I have log of 1 over z. Just write it as negative log of z. Okay? And then, sorry?
I was just thinking of the times.
Yeah, it's times, then you can write it, you can write it as this term minus n log of z. And this n comes because I have t from 1 to n. So I have n of those. So I have n times log of z. This becomes n times log of z. And I have another term, which is basically this term. Okay? So is it clear here? Okay, so we're just trying to write the log likelihood of this function. And now I just replace the definition of z. By definition, z is double sum over this energy function. Okay? So that's my log likelihood. Now, if I want to optimize my model, if I want to learn the parameters, I have to maximize this log likelihood. Means that I have to take derivative with respect to my parameters and set it to 0. And my parameters is B, C, and W. I have to take derivative with respect to these 3 variables and set it to 0. So in total, if I just show all of my parameters as theta, and I want to, that was my log likelihood that I computed. So I would like to take derivative with respect to this. That's going to be the derivative of the first term minus the derivative of the second term. So with respect to theta. So derivative of the first term minus derivative of the second term. So derivative of the first term, I have, first I have derivative of the sum. So it's going to be sum of derivative. So I'm going to have a summation over t equal 1 to n of derivative of this log. And derivative of log of a function, call it u. Derivative of log of u with respect to theta would be, sorry? Yeah, it's going to be basically u prime divided by u, right? So this go to denominator, and then I have to take derivative of this, right? Okay, that's what happened. I have derivative of t 1 to n, because it's derivative of the sum of the derivative. And this derivative of this log would be 1 over this u, which I have it here, and u prime. So I have to take derivative of this, which is summation of e to the power of a function. And e to the power of u would be u prime e to the power of u, right? So derivative of this times e to the power of this. I mean, the same term. The same term times derivative of this, which is derivative of this term with respect to theta. Okay? So is that clear? I mean, is that clear how we have taken derivative of the first term here? No? Yes?
So my only question is about the, you have listed a gradient with respect to theta right after the exponential at the top. I don't really understand that.
This is derivative of this term. It's not derivative of theta minus this.
Oh,
Maybe you need a bracket here.
Okay, I see.
Yeah, it's derivative of that term. Like besides this, is it clear what we have done? Do you want me to do it on the board, or you're okay? Okay, do exactly the same thing for the second term here. It's going to be n, and then I have to take derivative of this log. It means that this comes as a denominator, and I have to take derivative of e to the power of this function, which is going to be derivative of the function times e to the power of the function. So the e to the power of the function, derivative of the function. Again, it's not like theta minus. It's like it's better if I put a bracket here. It means that it's derivative of this negative energy function. Okay. So if you think, I have like 2 terms now. If you think the first term is expectation of this energy function with respect to this conditional distribution. And second term is derivative of this energy function with respect to this joint distribution. Okay? So, to see this, if I write like summation of x, I equal 1 to n. That's expectation of x if x has been drawn from a uniform distribution, right? If I write wi xi, that's expectation of x if wi's are basically, if if Wi, if it's a distribution, let me write it as P of xi, that's the expectation with respect to this distribution, right? But if it's not really a distribution, if it doesn't sum to 1 and I put W here, then I can normalize it. And that would be basically expectation with respect to that distribution. That's exactly what happened here. That we had this summation of this term, and then we normalize it as if this is a W. It's just a weight that we normalize. And the same thing happened here. That's a weight, and we normalize it. But this weight is, WH, WT is fixed. I show you an observation. And you are just sampling from H. But here, W and H, both of them are unknown in the second term. Remember, the second term comes from the fact that we wanted to compute Z, which is summation over V and H, right? So in short, I can write it in this form. And those who are familiar with undirected graphical model, this is not specific to restricted Boltzmann machine. It appears everywhere in, undirected graphical models, this form. That you have this expectation of the derivative of energy with respect, over H. But here, the second term is basically double expectation or double sum, because it's over H and V. Okay? So this term is easy to compute. The second term is, in most of the case, intractable. Because to compute this first term, I show you W, I show you V, an observation, and to compute this expectation, you have to sample from H. And then you have to sum over all values that you have sampled from H. It's linear, right? I show you one observation, you sample from H, sum it up. It's easy. But here, you have to sample from H and V, and then sum it up. And don't forget that why it becomes intractable, don't forget that we are taking derivative of maximum likelihood. It doesn't have closed form solution. I have to do gradient descent. Do gradient descent means for each of these parameters, I have to say W minus the derivative of this gradient descent. Now suppose that in each iteration, you want to compute this derivative. And for each iteration, you have to sample over H and V. And then, compute this expectation. Compute the sum and do the expectation. To sample from H and V, you have to do Gibbs sampling, which is easy to do, but it takes some time for, burning n period, until this MC technique, all of them, needs to mix well. You have to let a period goes until we get to the stationary distribution, and then we take that sample. And imagine that in each iteration, you have to do this. It becomes completely intractable, This part is okay. The first term is okay, but the second term is not. Okay. Okay, let's pretend that it's okay. If I take derivative of this energy function with respect to the three parameters that I had, it's easy to take the derivative. That's my energy function. With respect to W, it's going to be HV transpose. With respect to B, it's going to be V. And with respect to C, it's going to be H. Okay. Now, if I want to write basically my update functions according to gradient descent, then the total gradient, that will be my first term minus, this double expectation over this HW, or this double expectation over V, and so on. Okay, and this becomes problematic, as I said. Okay, to avoid this problem, there is an algorithm which is called contrastive divergence. So it's not an exact method, it's an approximation, and I don't know, it's a little bit hacky. I mean, it makes sense intuitively, and people have done some theoretical work on that. But the main intuition is that, okay, you want to compute this double expectation here, which is hard to compute. Okay, we can't compute it. Let's replace it with a point estimate. So I can't compute double expectation here. Suppose that I need to do a point estimate. Or suppose that, I mean, point estimate in a sense that if I want to compute the expectation only with 1 point. Okay, so that's basically the idea. That's the main idea here. So the idea of contrastive divergence is that replace the expectation by a point estimate at that point. And okay, what does it mean exactly? It means that, you know, I give you an observation V. Okay, using conditional distribution, you can sample H. Because you know pH given V. So I give you Vt, sample H. And sample, given H, you can sample another V. And given this V, you can sample another H. That's Gibbs sampling. You know, go a couple of iteration of Gibbs sampling. You have a point, call it V tilde. Use this V tilde in place of your expectation. I mean, put it in the derivative of the energy function. We were supposed to find expectation of the derivative of the energy function, right? It basically means over all values of V and H. Now, you don't need to sample all values of W and H. Sample 1 point as if you compute the expectation over only 1 point. Okay, so as an approximation. So the intuition basically is that if you look at this derivative, it has 2 terms. You know, think about each term, what each of these 2 terms are doing. I want to minimize the derivative. When I want to minimize the derivative means I want to make this term small and I want to make this term large, the second term large. This term, the first term, is a term about data. The second term is a term about the model. You know, the first term is based on my observation. And the second term has nothing to do with my observation. When I want to make the derivative small, means that I want to make this term small and I want to make this term large. So making this term small means that I show you an observation. Give me a representation of data, H, such that this configuration makes sense in a sense that it has low energy or has high probability. Okay? Yes?
Do you use an H tilde state as well for the rest of the derivatives?
Here?
Yeah, I mean, is the previous
Yes.
H point, that's
Yeah,
H tilde too?
yes. That's H tilde also. You know, suppose that my observation is this image. The first term basically makes sure that you find a hidden variable or a representation of tree which makes sense in the sense that this pair of configuration, this pair of data, H and V, minimize the energy function. But the second term should be large because it has negative sign in front of that, and if you want to minimize everything, that should be large. That should be large means what? Means that, suppose that I started the process. I initialize everything with some random values uniformly. If I sample V given H, given a random H, if I sample V given random H, what I'm going to see? It's not a digit given a random H. I'm going to see some noise. Okay? So the first term makes sure that if I show you an image, give me a configuration which minimize the energy. The second term basically tell me if I, the assumption is that the model has some, wrong belief, doesn't see the data. I have some random H and it generates some random V. The probability of observing this noise should be small. The probability of observing this should be large. The probability of the other one should be small. So basically in each iteration, you change the parameter in a way that it pushes down the probability of observing this type of data and increase the probability of observing this type of data. And if you want to do it exact, it should be expectation over all possible values of that. But if you cannot compute it, let's take one sample of the data that we don't like to see. What sample of this type of noise? And try to push the probability down according to this particular belief of the model or generation of the model. Okay? So it seems that it works pretty well in practice if you compute just this second term, which is a double expectation by a point estimate. Means that instead of this expectation, just get rid of this expectation, compute this derivative, and just use these examples that you have generated through Gibbs sampling, starting with an observation. This is usually called negative sample in this literature. So the idea of this algorithm is replace the expectation by point estimate and obtain the point estimate by Gibbs sampling. And you don't need to run this Gibbs sampling for a long run. Just do it for a few iterations. In practice, in fact, people shown that one iteration of Gibbs sampling would be sufficient in many cases. I mean, given V, generate H, generate V, and that's your negative sample, and go for it. It does work well. And another important thing that start the chain with your observation. Don't start it with some initial value. Start the chain of this Gibbs sampling with your observation. Okay. So that's the detail of the algorithm that I'm going to skip. Let me show you this example. This is MNIST digit, and if you train restricted Boltzmann machine, then and look at the weights that it learns, that's visualization of the weights. Okay, the visualization of the weights. And so how do you interpret this? As just think of this as features, the features that are supposed to explain your data. So one way, or the way that this paper explained this feature, is that it's like stroke of the pen. When you're writing different digits, it's just a stroke of the pen. So they just want to show that it learn interesting features. Okay, so now you can turn the light on. So what does that's restricted Boltzmann machine, and restricted Boltzmann machine, as I said, is building block of deep network now. So how it contributes in deep network, as I said, that was the first paper of deep network that appeared. But the problem with deep network originally was that we're not able to train deep models using backpropagation. You know, if I have many layers, using backpropagation, you're not able to train it. And that was the reason that no one actually trained a deep model. Until 2006, that Hinton actually trained the first deep model using this idea of Boltzmann machine. So the first deep model that was proposed was layers of Boltzmann machine. So these two layers are Boltzmann machine, these two layers, and so on. So it's completely unsupervised, right? So I give some input to this model, and I can compute a representation for this according to Boltzmann machine. So it gives me, regardless of what the output is, you know, I'm doing classification or regression or whatever, regardless of what the output is, I can compute a representation for this layer. Now take this layer as input, and this one as hidden, and this one as hidden. Now you can, you know, do another Boltzmann machine and find a representation of this layer. And layer-wise, you can go up and up and up, you know, and compute basically weights and representation of each of these layers up to your output. Now, think of all of these weights as initial values of weights, and now do some fine-tuning. Now assume that you have a full network, and these are your weights, but these are initial values of your weights. I want to give this input, take that output, fine-tune this, and fine-tune could be like same, you know, techniques like backpropagation, for example. That was the original idea. But now that we are able to basically learn deep models without this type of assumption, and by just backpropagation, by assuming that these activation functions are not sigmoid or hyperplane tangent anymore, but they are like linear rectified union, then there is no need basically to use Boltzmann machine as building block, and rarely people, you know, use it in deep structure. But it was common at the beginning of deep network, and since each of them is basically undirected graphical model, people used to call this structure deep belief network. So it's belief network, layers of belief network together, it's used to call it deep belief network. The first paper was about deep autoencoder. An autoencoder by itself is a structure in deep network that originally people and researchers used this Boltzmann machine to make autoencoder and deep autoencoder. But recently, you can have autoencoder without this Boltzmann machine. So I'm going to show you or tell you a little bit about autoencoder, but have in mind that autoencoder can be built using Boltzmann machine or without Boltzmann machine. And recently, people usually don't use Boltzmann machine to build. You know, the idea of autoencoder, just forget about deep network. The idea of autoencoder is that I have a layer of my observation x, which is a vector, and I have another layer which is has less unit compared to this x. So say, for example, x is in RD. Then I have h, which is in RP. And p is less than d. And then I have x again. Okay? So it's like a bottleneck. And then I have connection between all of them. So it's like a bottleneck. So suppose that it's I have a neural network and it's not deep, it's shallow of this form, and it's feed-forward neural network, but the input and the output are the same. So I give input, I would like to reconstruct this input. And I can have another restriction that people usually have. If this weight is W, I can tie the weight of this layer to be W transpose. This part is usually called encoder, and this part is called decoder. So that's why it's called autoencoder. So given X, I would like to reconstruct X. Okay? So, and then I will treat this part as, some representation of data in lower dimensional space, in p-dimensional space. So end of the day, I have learned a transformation W, which basically, when applied to X, it generates H, and X is D by 1, and this is P by D, so it generates P by 1. So it maps the data in lower dimensional space. So we have, say, for example, PCA that maps data in lower dimensional space. So we can assume that autoencoder is something similar with the structure of neural net. Okay, in fact, you can mathematically prove that if you have a simple linear autoencoder, the bases that this autoencoder computes span the same space as eigenvectors in PCA. Okay, so basically, in a sense, they're identical. This is PCA. It's doing PCA. And another way actually to get some insight about the problem is that PCA, if you want to compute PCA, you can compute PCA by maximizing the variation of each direction, or you can compute PCA by minimizing this cost function. Or let me write it this way. It's xi summation over I. I would like to minimize it this way. Subject to the constraint that U transpose U is identity. If you try to solve this optimization problem, the solution is eigenvectors of covariance matrix if X is centralized. Okay? So compared with this structure, that's exactly what's happening. U transpose X is a transformation of X. And if U is D by P, U transpose would be P by D. It maps everything to P dimension. Then this is orthonormal matrix, so U would be the inverse of U transpose, or the inverse of this projection matrix. It's projected back. So U will be like D by P projected back to the original space. So as if you projected to lower dimensional space, you projected back. Exactly, exactly the same thing that we're doing. You projected to lower dimensional space, projected back to original space. And then we are trying to minimize this cost function, exactly the same cost function that we are trying to minimize here. Okay? So there are papers in the literature, not recently, in the past, that people try to make it nonlinear by adding some sigmoid function, for example, in this layer and so on, which is not helpful at all, because mathematically you can prove that the optimal solution to this problem is PCA. And basically, it means that the optimal solution here actually is linear. If you want to minimize this cost function, you don't need any nonlinearity to be applied here. Okay? So the paper actually that was published in Science and made deep network, as a field, was sort of deep autoencoder. If I have many of these layers, and if I have many of these layers, we were not able to train it, but by assumption that these are Boltzmann machine, they train it. That was the first deep structure that was trained. Okay, but now you can have a deep autoencoder without Boltzmann machine, and people use this for dimensionality reduction. Okay, so it could be an alternative for dimensionality reduction, and in fact, it produces very good results. Okay. So if you have many layers, then you need to apply some nonlinearity here. Because if you don't have any nonlinearity, then it's going to be a linear transformation, linear transformation, linear transformation. It collapses to one linear transformation. So it's exactly the same as PC.
Okay.
Nothing happened. But if you have many layers, then you need to apply some nonlinearity in each layer. Okay. So in the literature of autoencoder, this type of structure is called under-constrained autoencoder. So over-constrained autoencoder doesn't have this structure of bottleneck. In fact, here that was D, that was D, and that was P, but P was less than D. So what if P is greater than D? Okay, so what if this is the structure? So this is my X, and this is my X, and H is larger than this. Okay. So if I train a network of this form, what does H is going to learn?
High-level representation.
Sorry?
A higher dimensional representation of the data.
Is it going to be higher dimensional representation?
Would it be almost lossless? And you basically would sometimes have like some entries be zero, or basically have redundancy.
Yeah, exactly. It's first of all, you're not going to lose any information. Here, you're going to lose some information because you're going to lower dimensional space. Here, you're not going to lose any information, but as you said, it's going to be either redundancy or exactly the same values copied on H, because what's the most trivial way to do this reconstruction? Suppose that I have some units here, and I have more number of units here, and I would like to reconstruct X. So the most trivial solution would be to copy everything from this node to this node, from this node to this node, from this node to this node, and then copy them back, right? And set the rest to 0, for example. So that's the most trivial solution. And if you do gradient descent, on a feed forward, it's going to learn something like this and can reconstruct everything perfectly. So by itself, it doesn't learn anything useful in this hidden unit. But there are some variation of that could be useful. And one of them is called denoising autoencoder. Denoising autoencoder add a layer of this form, that if I have X here, then I make a layer to X tilde when X tilde is noisy. It's not the same as X. Okay? It's noisy. And the output is X, noiseless. Then H could be a useful set of features. And this noise could be any part of noise, could be additive noise, for example, or you can basically train this model such that this noise is setting some values of this X to 0, say X is 1 and 0, It's black and white image. And just ignore some of these values as if you haven't observed those. Another way to basically learn something useful in this structure is to add a term as a regularization term to the cost function. So I have a cost function that needs to be minimized. And this is based on my observation x. So distance between input and output. So we can add a regularization term here to avoid this trivial solution. And that's the regularization term is basically derivative of h with respect to x. It's a Jacobian matrix. H is a vector, and x is another vector. It's a matrix, so the norm of this. Okay. So in the case that we had this trivial solution, it means that h was a copy of x, right? So if I change x, h will be changed immediately. So this derivative basically tell me how much h is going to change when I change x. I would like to penalize the case that h change radically when I change x. I don't want this to happen. You know, I change x, but I don't want h to change immediately or radically. You know, so basically you have the cost function and you penalize it with this variable, and in over constraint, you know, that's denoising is one structure and it's another structure. It's useful in some image processing tasks. And if you remember, I suggested a project as final project to apply this to natural language processing. When denoising, when noisy data was not a noisy image, but it was noisy, say, translation, or noisy sentence, and you want to make it correct. Okay, any question? Yes?
In the nonlinear autoencoder that you had before, which was still P less than D, is there any restriction on any of the matrices in each layer being orthonormal like that?
No. No. No, there's not such a restriction, and that's why it doesn't exactly find the bases that PCA finds, but it finds bases that span the same space as PC. Okay, so let's get back here 3:30.